Good evening, everyone. Okay, good evening, everyone. Uh, we have waited for I think 10 minutes and it's already 7:10, so I think we should start our session now. So I hope if you guys have any questions, if you wanted to ask some questions, you can ask regarding the weekly lectures which has been uploaded on the NPTEL. Or otherwise, if there are no questions, then we should proceed for the session then. And you can ask your questions in the chat box here itself, so that will help in reading me the message, and others can also benefit from your questions. So, okay, so let me share my screen now. Okay, okay. So once again, good evening, all. Welcome to the live session of non-conventional energy resources. This is NPTEL course, and this is live session 8 being conducted on 28th of March 2023. The course is taught by Professor Pratap Haridos, and this live session is being conducted by me. I'm Rohit. I'm a scholar in IIT Bombay. So, how? Okay, somebody wants to join. So, I hope I am audible to you all. So, if there are any queries or anything you wanted to ask, you can post your queries in the here white in call messages. Other, I can read these messages and I will answer accordingly. Okay. And in between, if you have any queries from the live session slides, you can always free to ask. Please feel free to ask. Okay, so how I planned this session? I will first try to solve the non-graded part of the assignment, where we will discuss basically the non-graded part of the assignments are regarding the conceptual questions. So we will discuss the concept that are behind the graded part of the assignment. After that, we will move to the graded assignments and we'll try to solve those questions. So graded assignment questions are basically from the weekly lectures itself. So if you have gone through the weekly lectures, most of you will be able to solve this graded assignment very easily. Okay. And if there are any queries, any questions, or any interaction you wanted to ask, so you can ask in between the session. The queries are always welcome. Now moving to the question one, the blades of windmills experience cyclic loading and hence must have excellent fatigue properties. So actually, if you see this question, the first thing is that key blades of windmill. Okay, these thing you must have been known. Even if you are not gone through the lecture slides, the blades, what are the blades of windmill? What is a windmill? You must have known from the figures from different textbooks, other source of information. But the main thing is technical word is cyclic loading, okay? And another technical word is fatigue. So these two words, if you know these two words technically, you know what is fatigue, what is cyclic loading, you can easily answer this question. It's not a very difficult question. It's basically based on the concept of cyclic loading and fatigue properties. So yeah, the blades of windmill actually experience cyclic loading mainly because of the movement of the blades and due to the wind itself, and also must have excellent fatigue properties. So I will discuss more about this cyclic loading and fatigue properties. So basically this cyclic loading, the is a type of loading that actually leads to fatigue, and so it's a true statement. So let's move to the second slide, which will explain these concepts of cyclic loading of fatigue properties to a much better extent. Okay, so this is a cyclic loading. So cyclic loading is basically, if you want to define a cyclic loading, so cyclic loading is basically defined as a continuous and repeated application. So I have made this word bold: continuous and repeated application. So it must be continuous and it must be a repeated application, not that some stresses or some load are applied at an instant, then this load is removed. Okay, so that is not a cyclic loading. That may induce tensile stress, that means induce tensile strain or compressive stress strain, but it cannot be called cyclic loading. It has to be continuous, it has to be repeated. So what is repeated? What is something that is called repeated? So it must have a particular time period of application. So if it is applied at a instant t equal to 0, then after 2 second, after 4 second, after 6 second, 8 second, 10 seconds, so it will go on. Okay, so that is something which is very much related to cyclic loading. Okay, so cyclic loading is defined as continuous and repeated application of load. It must be a load. Okay, so load is basically something, some amount of force that is applied to a body. So that will induce a fluctuating stress, strain, forces, tension. So these four things can be called load. Okay, stresses and strains are somewhat different from load, but as of now, for simplicity, these are all basically what you say, function of load or something you can say. Somebody wants to join. Let me see. Let me add him. Okay. Okay. On a material or on a structural component. So what is a structural component here? Material, anything can be called material. Basically, it can be metal, non-metal, or anything, ceramics, everything. Or on a structural component. So when we have links and joints, so overall these things are called structures. Okay, made up of links, joints, various bends. It can have movement altogether with respect to each other. Okay, so that is called as it can be fixed also. So that causes degradation of the material. So it must cause degradation of the material and ultimately leads to fatigue. Okay, so cyclic loading is something that leads to fatigue. So cyclic loading and fatigue are not so much different in sense. They are very much interrelated to each other. So if you see this graph has been taken from ResearchGate. I put this graph to make you understand what is basically can be called a cyclic loading. How does it look like? So there must be a load. So there must be some minimum load and some maximum amount up to which it can go. Okay. And there are in between minimum and maximum, there will be a mean load. So this thing is called, this is a graph in which x-axis is represented by time and q is basically you can take it as load here. Okay. So in between minimum and maximum, there will be a mean load. About this mean load, this load will be fluctuating here like this. So it is fluctuating from minimum to maximum, then again maximum to minimum, and this whole thing from crest to trough is crest to crest. Okay, crest to crest or trough to trough is called time period of the oscillation or time period of application of load. So it looks something very much like this if we talk about cyclic loading. Now we came to the word fatigue. So fatigue loading is primarily the type of loading which causes cyclic variation. Okay, so you can see here, I think I messed it up. Okay, so which causes cyclic variations. So in the earlier slide, you saw that there was a cyclic loading, and basically these terms are very much interrelated. In the cyclic variation, in the applied stress or strain or a component. So stress is something which is applied force and there is a internal reaction to that force. So stress is generated. Strain is something when we see basically an application of that force on the primarily the length volume. So there must be a volumetric strain or tensile strain or compressive strain type of thing, and this any variable loading is basically a fatigue loading, so it has to have a variable loading, so it varies between minimum to maximum. As we saw in cyclic loading, it varies from minimum to maximum. So there can be three types of fatigue loading. One is fully reversed. You see that above zero is positive, below zero is negative, and it is fluctuating between positive and negative. So many of you may ask a question here. So like how can a force be negative? Okay, so I think most of you have not gone through in detail to this picture. So there is a question: how can be a force be a negative? See, magnitude of force is preserved here. Only the direction is reversed. Okay, so if we move forward, the force is applied in the forward direction, then we take it as positive force. Okay, then if it moves to the backward direction, the force application of force, then it is negative. Okay, and it has a very different effect on the body also. So that's how this fully reversed. Here it is repeated, not fully reversed. Why? Because you can see the force is above the zero. The force is positive, but it is repeated after some time interval. Here it is fluctuating in between some positive value to some mean value. Okay, so it is fluctuating to some mean value. It is above zero, not exactly to the zero. Here it is repeated because after some time interval it is getting zero. Okay, so most I think these two graphs are very much related to each other. Not so much of difference can be seen between in these two graphs, but in fluctuating there is actually a fluctuation in the value of load actually. Okay, so I think now you have a much clear understanding of what is cyclic loading, what is a fatigue. So this question, the blade of windmills experience cyclic loading and hence must have excellent fatigue properties. So it's a true. You must have got a good sense now. So I've also put some extra information about fatigue so that you guys can have a good knowledge about fatigue. If there is anything or any question asked in the exam, you can easily answer. So factors affecting a fatigue life of the component. So there must be a loading condition which affected like type of stress. What is the type of stress like compressive stress, tensile stress? Okay. What is the amplitude? Amplitude, you know, how much is the variation, maximum variation of the stress? Mean value, how much is the mean value? Condition of the specimen as structural member is also like corrosive member cannot have a very good fatigue life. Okay, but it can fail. Okay, so stress concentration, surface finish, corrosion or something. Okay, material. What is the type of material? Okay, thermal. How is the thermal history of the material? Like grain size in the metals. You will study more about this grain size when you will go through the crystal structure of the material, the lattices, everything. Okay. Environmental conditions. Yeah, temperature actually affect the fatigue life of the material very much. So there is a creep stress that comes into this picture. So we'll not go much detail into that creep stress and we'll focus only on fatigue life. Corrosion effect, as I have said earlier, the corrosion affects the fatigue life of the material. Okay, so this question is over. If there are any doubts which you want to discuss regarding question one, you are welcome to ask. So I will give you guys some time to focus on this three slides, so that you can ask your doubts. Okay, there are no questions. Okay, so no questions now. So I will move to the next question then, which is question 2. Question 2 basically asks about the beds limit. So I think someone who is studying wind turbine, so this beds limit is very important when you talk about some wind turbine. So beds limit represent the minimum efficiency that a windmill must have to be commercially successful. This is a false statement. Why it's false statement? Because bed limit doesn't talk about the commercial successful application or some minimal efficiency. It says how much a wind turbine can produce, how much power a wind turbine can produce given a velocity of wind. Okay, so that is about the bed limit. So let's talk about some bed limits. So Bed's limit is basically based on Bed's law. So Bed's law actually was published in 1919 by a German physicist named Albert Bedge. So don't confuse it with Albert Einstein. He's different. Albert Bedge is different. So Bed's law indicates the maximum power that can be extracted from the wind. Okay, so see here what I talked in the last slide. So it's not the minimum efficiency, it's the maximum power that can be extracted from wind, independent of the design of the wind turbine in open flow. So Watt's law doesn't depend on the design of the turbine. It only talks about if wind is flowing with some velocity, then maximum power that can be obtained from a wind is basically defined with Watt's law. So let's see what this significance of Betts law. So according to Betts law, no turbine can capture more than 16 by 27. Okay, so this is a ratio 16 by 27, which is quite equal to 59.3% of the kinetic energy of the wind. So if the wind is flowing with velocity, so how much is the kinetic energy of the wind? Half mv square or rho a v square. Okay. So this factor 16 by 27 is known as Bed's coefficient, and the practical utility scale wind turbines achieve at peak 75 to 80% of the Bed's limit. So actually we can get 59.3% of the power of the wind that can be captured kinetic energy of the wind, but still with this belt law, we are not able to achieve this 59.3% also. We can only reach 75 to 80% of this 59.3%, something around 45 to 50%. Okay. So this is actually a technology gap, and more research is going on between this technology gap. Okay, so let's move to the next slide where I will make you explain this in visual terms, so you will get a good idea about this wind turbine thing. So let's say wind, there is a wind flowing and this is a wind turbine, and which type of turbine is this? Can anyone say here? It's basically a horizontal. I'm writing here horizontal axis wind turbine. So this is basically horizontal axis wind turbine. So let's assume that wind energy has 100% total of the wind energy available to harness. But with Bell's law, we can see that only 59.3% of this wind can be maximum utilized, wind power can be maximum utilized. So 40.7% is actually lost to the to the wind with the wind itself. So only 59.3. But of this 59.3%, only 70% can be converted to the electricity. So what is the conversion actually? So it's zero point 0.7, that is 70% into 59.3. So you can multiply it and got the value. How much should be the conversion if we have 100%? Then it will be something around 50% or something. You can calculate it down. Okay. So this is the actual how much energy that can be harnessed from a wind. So before moving to question 3, what I will do, I will leave you guys with this slide. So you guys can actually have a good understanding about the concept which is discussed here, that is Bates law. And I want you guys to ask your queries in the chat box so I can read them and answer them appropriately. So yeah, please focus on this. Okay, so let's move to the next question, guys. Hello, sir. How can I get my hall ticket admit card? Rishikesh, it will be generated and will be sent to your mail itself. So that's where you will get your admit card if you have filled the form. So don't worry about it. You will get your hall ticket admit card on time. Okay. So before exam, I think some 4 5 days before exam, you will get your hall ticket admit card, and it will be near the center which you have chosen. Okay. So don't worry about it. Let's move to the next question. In drag type of wind turbines, so yeah, the concept here is drag type of wind turbines. The tip speed ratio, what is tip speed ratio? We will it can be greater than one. No, it can't be greater than one. It should be less than one. Okay, for drag type of wind turbines, it should be less than one. Lift type of wind turbines, it will be greater than one. So the correct answer is actually false. So it's a correct answer here. So let's move to the next slide where we will discuss about the type of wind turbine because there is here discuss drag type of wind turbine. After that, we will move to the discuss tip speed ratio. Okay. So basically, drag type of wind turbines are also called Savonius turbines. So then generally they have rotors with solid vanes. Okay, so this is drag type of wind turbine, Savonius turbine. So there is a rotor with solid vanes and that rotate about a vertical axis. So this is the vertical axis and about it this rotates. Okay. Left type or Darius type. This is the Darius type of wind turbine and they have toll vertically airfoil, so you can see the airfoil here. They take this study this curve, so this is basically airfoil style. Some appear to have been an egg beater shape also. So yeah, this is what it looks like. And tip speed ratio is basically the ratio between the speed of the tip of the wind turbine blade and the speed of the wind itself. Okay, so this is basically the speed of the ratio between the speed of the tip of the wind turbine blade and the speed of the wind. So now you get it. This is basically speed of tip of the wind turbine blade upon speed of the wind. V wind. So basically, let's see if this is wind turbine. So at the tip, what is the velocity? And with the velocity of wind, it divided. So that is tip speed ratio. It's a very important concept. For example, if the tip of a blade is traveling at a speed of 100 mil per hour and the wind speed is 20 mil per hour, then TSR is 5. How it is calculated? 100, that is velocity at the tip divided by 20. So it is equal to 5. You can see here 5. Now basically this question was about drag design. So this is drag type of turbine. So basically V tip upon V wind is less than 1 here. So V tip at its maximum can only be as much as the V wind. So at the maximum value of V tip can be as much as the wind. So this is basically typically V tip is generally less than 1 for drag type of wind turbine. So that's why if you divide this V tip by V wind, take this wind V wind here V tip, so it will be less than 1. Okay, so I think you must have got it quite clear. So before moving to question 4, I think this is an important concept, so I must wait for your questions here. So if there are any queries, any questions you want to ask, you are please feel free to ask. Okay. If there are no queries, so basically it's asking that two blade horizontal axis wind turbine experiences uneven forces due to presence of tower. Okay, so yeah, this is actually a true statement. So basically wind turbines are horizontal axis wind turbine have this type of shape, and this is the blades. So it basically experiences uneven force due to presence of tower. A tower is there in this direction. So basically there is a force here mg for this tower, and the force drag here, drag. So it's basically uneven type. Okay, so it's quite true statement. So please have a look at this question for some time, and if there are any queries, please feel free to ask. Okay, now moving to the next question. Let me see if somebody wants to join. Okay, no one wants to join. So moving to the next question. Modern windmill uses blades made of concrete. No, they don't use a blade made of concrete because concrete has a very high material density. If such high material density blades will be used, then blades won't be able to move. So something which has a very high strength to weight ratio is used. Basically, a composite material used to make blades. Stainless steel is also preferable. Aluminum blades are also there. So aluminum, stainless steel, composites. So these blades are actually preferred rather than having a blade which is concrete. Okay, so this is basically a false statement. Okay, so I think with this the graded part of the assignment is over. So I will suggest you guys to go through this from one to question number one, two, three, four, five. So you will have a good understanding of the different concepts here. Then we will move to the graded part of the assignment from questions 6 to question 15. We have graded part of the assignment here. So now we will discuss that only. Okay. Okay, so now let's see if anybody wants to join. Okay, so let's move to next question then. Okay, so we have completed our grade non-grade part of the assignment. Now we'll move towards the grade part of the assignment. So these questions are basically conceptual questions. So if you have your concept clear, you can easily answer. So formula for calculating the wind power is, so you have seen in the weekly lecture slides itself that if you want to see the formula for calculating the wind power, it is basically half rho AV V1 square minus V2 square. Okay. So even if you don't know the formula, it can be very easily derived. Basically, it's basically derived on the kinetic energy. So kinetic energy is basically half mv square. M is basically density into rho AV. Okay, so this term half rho AV and then this V1 square minus V2 square. So it was quite easy. The correct answer is answer C. Okay, now moving to the next question then. Bed's limit is the dash maximum efficiency for a wind turbine. According to it, only percent of kinetic energy which can be used to spin the wind turbine. So I think it was quite clear in the second slide or third slide itself. Like bed limit is basically the theoretical maximum efficiency, not the experimental maximum efficiency. And according to it, only 59.3% of the kinetic energy is actually used to convert spin the turbine to generate electricity. So the correct answer is answer B, not these. Okay. Okay, moving to the next question. If V is the velocity of the wind, the energy available in the wind is proportional to. So, in the previous question, also, I think we have seen that energy of the wind is basically kinetic energy of the wind. So, it's proportional to uh, half rho A V square. So this V square is basically this. So the correct answer here is answer B itself. Moving to the next question, if the wind velocity is 20, then tip velocity can be 60. Yeah, it can be. For basically lift, there were two type of turbines, lift type and drag type. So for lift type, the tip speed ratio can be greater than 1. So yeah, wind velocity is 20, then tip velocity can be 60. It's true statement, okay? So it's true. Moving to the next question. Windmills are usually positioned. So basically, windmills are like there can be many type of windmill, horizontal axis, vertical axis. So basically, they are placed such that there is a sufficient space between windmills because there is a tower, there is a requirement of space. Each windmill generally requires zero point 0.5 square meter of space. So there should be a sufficient space between windmills to avoid air turbulence from one windmill affecting the other because the air is passing through it, it can affect this windmill. Okay. So the correct answer for this is answer C. Moving to the next question. Gearbox used in the windmill is typically fuel. Basically, gearbox, what happens? There is a hub, there are blades. So this hub is connected to a shaft, and but the rotation of this shaft is quite low. So there is a gearbox, a big gear here, a small gear here, and this gearbox is connected to generator shafts. So low RPM at blade, yeah, the low RPM at blade and higher RPM at generator. So the correct answer is answer C. Gearbox is used in windmill to typically ensure low RPM at blade and higher RPM at generator. Okay. Okay, moving to the next question. Select the statement which are actually true. So if you read the statement, tip speed ratio is a ratio of linear speed of tip to this is correct statement. Statement A is correct. Tip speed ratio is greater than 1 for push design and is smaller than 1 for left design. Galat. This is actually wrong actually. Okay, for drag design it is greater than 1, for left design it's less than 1. Okay. Sorry, opposite. Tip speed ratio is smaller than 1 for put in. This is correct statement and greater than 1 for left as we have studied in the previous slide also. And speed of blade is more at the center than at the tip. This is wrong. Okay, because speed is V equal to R omega. As the R increases, the speed will increase. So it will more at the tip than at the center. So correct answer is A and C. On to the next question. What is the significance of three blades in windmill? So basically, if you see the windmill, in comparison to one blade, three blade actually use the interaction, increase the interaction of wind. So this is correct statement. Also, because of more number of winds, higher torque is actually generated, and basically because of this design of three blades, the distribution load on the shaft is more uniform than one blade windmill. Because if we have one blade and we have to attach a counterweight here. Okay, so all of these three statements are actually wrong. So the correct answer is A, B, and C. Horizontal axis wind turbines. So horizontal axis wind turbine has actually access stronger winds because they are situated at tower, are often mounted on tall tower. This is also correct. Usually have blades that are pushed by the winds only in part of their rotation. This is a wrong statement. They are not pushed only part of their rotation. They rotate as a whole. Capture wind energy through rotation. So yeah, correct answer. So the correct answer is A, B, and D. Now moving to the last question. Where and why is the pitch bearing used in the windmill setup? So if you see the pitch bearing, there is a hub where blades are connected. So yeah, its blades are attached to it through bearing. Hub and blades are linked using this. Yeah, this is also correct. It reorients the blade. Yeah, this is also correct. It increases the RPM. No, pitch bearing doesn't increase the RPM. So the correct answer is A, B, and C. Okay, so with this, all the questions regarding the non-graded part of the assignment is completed. Uh, sorry, graded part of the assignment is completed. Okay, and so we have some time also left. So we'll discuss some concepts also here. I have added two slides regarding the concept. So after that, we'll end this session. Okay. So I want that key you guys should focus on the last two, three questions. And if you have any queries, you can ask here. So basically, I have added here some question concepts. Basically, most of the time we discussed about the kinetic energy. So yeah, kinetic energy basically represented by half mv square. So yeah, kinetic energy, if we convert m into, it can be called density into volume. That is mass equal to density into volume here. And volume is basically area into length. So if we differentiate it, we will get half rho av cube. That is the power generated from wind. Okay, so if we see the power as a function of wind speed, basically. So as the wind speed increases, which we can see here, so there must be some minimum wind speed like 16 kilometer per hour to generate power. Okay, so it cannot be that at any wind speed power can be generated. With this, there is some exponential increase in the power as the wind speed increase. So this graph is very important which depicts the power as a function of wind speed. Okay, so please look at this graph and the previous equation, and if there are any questions, you please feel free to ask. So I think if there are no queries as of now, okay, no queries. So yeah, we can end the session. So we'll wait for some more time for any queries to arrive from the students, and then we will end this session. Okay. Okay, so if there are no questions, let us conclude this session then. So if there are any questions, you guys are feel free to ask in the discussion forum. And please go through the videos. These videos are lively recorded and will be uploaded on the YouTube channel. The link will be shared with you in the problem solving session tab. So, okay, once again, thank you all for attending this session. We'll meet on the next Tuesday. Thank you once again.